Hello and welcome to another video. In this video we're going to be continuing on with the TypeScript line 75 and we're going to be doing Subtree of Another Tree. So this problem is pretty straightforward. You have a tree and you have a subroot and you are asked to figure out, is this subroot equivalent in structure of any node of this tree to the left? So here it is, because if you start from this node and you compare it to the subroot, they are the same tree. So essentially you need to traverse the tree, and for every single node you need to compare it to the subroot and see, does it have the same structure? And then for this one, you would traverse and you would say, well, there isn't really a node, so you try to compare these, but these don't have the same structure, right? Because this is not the same as this, because we have this extra node. So because this is an easy problem, we're just going to do like a basic way of doing it, essentially. And all we really have to do is traverse the tree, right? So we can just do like a DFS of our main tree, and then for every node, compare that node and subtree to the subroot. And so you can just write like a comparison function that just takes two nodes, essentially. That just takes two nodes and essentially just compares to make sure that like their nodes are equal. So for example, let's say for this, let's just look at like this example, we'd say, okay, let's compare 3 to 4. Well, 3 and 4 aren't equal already, so we can just return false. So for all of these, we would just return false, but essentially the function would take two nodes, and it would basically have to be that the node values are equal, and the left and right subtrees are equal. So that's just like a pretty easy comparison. Check two trees for equality, right? So like, for example, here they would be unequal, so that would be false. Then you would check the right child, and this would also be unequal, so that would be false. Then you would check the left child, and you'd say, okay, well, let's compare from the top. So 4 and 4 are equal. Now let's go left in both. These are equal, and these are equal. So for the comparison, the value has to be equal, and the left and the right subtree has to be equal. And you just have to find one node in our tree that's the case for. If there's one node in our tree that's equal to the subroot, where you do the whole comparison, then you do return true. And that's pretty much it. You just traverse your left tree, and for every node you just compare starting at the root of the other tree. You just make a helper function to compare two trees to see if they're equal. And yeah, that's pretty much it. So now we can code it up. So what we are going to do is we're going to have two functions. We are going to have a comparison function. So we could say like const compare, and it's going to take two nodes. So we could say node 1, node 2. And we should probably give types of these. So these nodes are both going to be tree node null, tree node null, tree node null. And what's going to happen here is if the two values are not equal, right? So basically if node 1, or sorry, not if two values are equal, if one of these is null, so if not node 1 or, too much Python, or not node 2, so if one of these is null, then basically there's two conditions, right? Either they're both null, or one of them is null and the other one is a node. So we can just say return node 1 equals node 2. And this would be true if they're both null, and if one of them is non-null, this would be false. So that part is fine. Now essentially all we have to do is we have to return, the values have to be the same, right? So node1.val equals node2.val, and the left subtree has to be the same, so we're going to recurse left here. So we're going to say compare node1.left and node2.left, and the right subtree has to be the same. So compare node1.right and node2.right. And so if these are all true, then this should be node2.val. So there we go. So if the two values are equal and both recursions are equal, then these nodes are equal. If any one of these is false, then the whole thing's false. So that part is done. That's our comparison function to compare two trees. Now we just need a basic DFS that will traverse down the tree and call this comparison function on every single node and this subroot node. So we're going to have DFS. It's going to be a function that's going to take a node, and it's going to be tree node null. Tree node null, and it will return. So if the node does not exist, then we can't, like the subroot is not as a non-null node. So if the node does not exist, we can return false right away. And if the node does exist, we can return traverse, or it's actually going to be compare of node and subroot, or the left or right of it with subroots, all right? So we say node, this should be subroot capital. So let's just compare the node's value with the subroot. If that's true, that's fine. Or we can DFS left. And if that's true, or DFS right. If any one of these is true, right? So like if the node's value is equal to the subroot, fine. If when we DFS left, that value is equal to the subroot, then that works as well. Or if we DFS right, that value is equal to the subroot. Any one of those is, all of those is fine. And now we just have to call return DFS, and we have to give it the root. And there's other ways to do this. You can also turn your tree and subtree into a string, but this works as well. So does work. And it is a valid solution. So let's go over the time and space for this one. So essentially what you are doing is you are going through every single node in your tree, which is O of n, right? Where n is like the length of your tree. And then you are comparing it to every single node in the subtree. So it's like n times m type of a thing, I believe. Now, like I said, you can do this. Is it more efficient? I think it is. It's about the same with strings. But yeah, this is basically O of n times m, where m is your subtree, like number of nodes, and n is your main tree number of nodes. And for space, so this is just the recursive stat call here. And basically, the farthest down you could ever DFS is gonna, like, your main trees should be bigger than your subtree. Yeah, because if your main tree is smaller than your subtree, then you'll always run out of space in your main tree. So I think the space depends on the main tree, which is just O of n, right? Like, worst case, your tree's all, like, has a right child or something. So it'd be something like this. I think this is correct. And yeah, I think with a string, it would also be similar-ish, because you would essentially have to compare every single node with the subtree and then recurse down and so on. So it would be kind of a similar scenario. And yeah, and because these constraints are pretty easy, because it's an easy problem, you know, it's fine. So yeah, this is going to be all for this one. Hopefully you like this one, and definitely, yeah, I think you should definitely know how to compare trees, and I think this is like pretty straightforward. And if you did like this video, please like it, and please subscribe to the channel, and I'll see you in the next one. I don't think we have too many more of the blindside you have to go. I think we have like 2 or 3. So looking forward to finishing that up, and thanks for watching.